Okay, I swear I wasn't going to do this, but listen. This is an hour and a half of my life I'm never going to get back. I got to come up with a better way. It took me an hour and a half to print the last labs. I opened it up to see if it was locked here, and I typed in either locked or not locked. You have to have one submitted that's locked and one that's not locked.
So how do you know which one you did yesterday?
So this is not yesterday. This is the one before that. Okay, so I'm going to hand this around. I wasn't going to do this, but I'm going to hand this around. This is in alphabetical order. This one says not submitted, so I know Logan doesn't have a locked one submitted. You should have one in here that's locked and one that's not locked. Right? And I need to get that graded. So it took me, literally an hour and a half during lab to print these. So the one from yesterday, you should be able to submit now. I guess I screwed up because it had the formulas in there in the white. Did you just type over that white stuff down below? Yeah, and the percent error. The rest it probably calculated right. Yeah, the rest it should have calculated right. The percent error, I had the percent error in for maybe only copper. Yeah, so you typed, did you guys type over the percent error column? Nope. Nope. So then all of those that will unlock, I will send you a locked one. We'll do the same thing. Yep. Literally, like this one here, all you had to do for the locked one is you put this in and just resubmitted, right? And then it calculated them all. So, okay. So that's that. Send that around. You should have a locked and an unlocked. We are going to do quiz question. Which one? 15. All right. Let's try 15. Okay. So this should be our last calculation of QT is equal to KA T2 minus T1 over D, I'm hoping, the way it looks. Am I missing anything in that? It's one equation I don't use a ton. Let's see. Yeah, that's right. Now, so this is number 15, the last one. So our thickness, we want this to be in meters. So this is going to be 0.005 meters. The temperature outside and inside differ by 30. And we need this constant for glass. That constant for glass, that K constant for glass, for heat at conduction. What is the answer in? They're in joule. It looks like megajoules, so we need joules. All right, so for glass here in joules, 0.84 right here. So zoom in on this. If you're watching, 0.84 we're going to use here for glass, and that's in. So this is joules over seconds times meters times degrees Celsius, right? Oh, that's the units for K. Joules, seconds, meters, degrees Celsius. Our surface area on that is, we actually have to calculate the area because this is 3 meters by 1.5 meters, so that would give us our area. And then we just need our time. Well, you're just going to multiply this to get area, right? Oh, let's see. If you did, it's going to be 30 degrees different. So I would just look at that as because if you're going from minus 10 to 20, you know you're going to have to go up 30 degrees. So I don't know if it really matters which one's T2 and T. I would just put 30 in there, the difference. The absolute value of the difference. Yes. Yes. It's, this is just cross-section area, I think. The area exposed that it's going to go through. Now this time is 1 hour. So 1 hour, how many seconds? How many seconds? Because we've got to have seconds here, right? How many seconds for time? 3,600 seconds, right? 3,600 seconds in an hour? That should work. Okay, what else do we have? Now we're bubbling this quiz again tomorrow. What else do we have on this baby? I
have no space here. Sorry.
What do you mean 11?
Okay, 11.
They would be 1,000,000 joules in a megajoule. So at the end of this, the answers are in megajoules. Mega would be 1 times 10 to the 6th. Kilo would be 1 times 10 to the 3rd. So megajoules is going to be 1 times 10 to the 6th when you get all done. All right, because the answers are in megajoules. When you get all done, a mega is 10 to the 6th, a million. Ow. But which one are we doing? 11. Okay. So in 11, we're going to do the rise in temperature of water that had fallen down a waterfall on Mont Blanc. What maximum temperature rise would one expect from a vertical drop of 20 meters? Okay. So we know that the vertical drop is potential energy. That's going to have to go into heat energy. This potential energy, how do you get potential energy? MGH, right? MGH for potential energy. So we know that MGH has to go in the heat energy, which is going to be MC delta T. And it doesn't mention how much water, so good, that can cancel out. And it looks like, what is the maximum temperature rise? Well, that would be our change in temperature, right?
For the hot tea one,
Yes.
is specific heat the same as water?
Yes. On 14, yes.
So back to 11, that would basically be GH divided by C, right?
Yes. Yep. And C is 1. Well, let's see. No, this is going to be in joules. This is going to be in joules here. Let's see. How do we get this? Let's make sure we better use, because GH is going to be, this would be joule units here. So let's double check, because this would be in joules if we calculated it out, right? Potential energy has always been in joules, so if we're in joules, we're going to use for this 4.184, right? 1 kilocal or 1 calorie. 4.184. I think our book is using 4.186. But what else do we have? Okay, we're good. Okay, let's go over to homework. How about on this? Nothing on homework? Okay, nothing on homework? All right, we are done. Yes, on 11. Back to 11. Yeah. 11 comes out to be, what'd you get? 46 degrees, huh? Hmm. What's that? Yeah, kilograms. Yes, because this right here, joules is kilograms. This is grams. Yeah, so we'd have to use 41.8. Yeah. Okay, what else do we have on this? That's it. Homework? Nothing on homework. All right. We are going to do then on with
Yeah, the next exam's the check.
technically. So does everybody have this on waves? Everybody's got this on waves. Okay. So since we're going to start wavelength, frequency, and all that stuff, this I did a long time ago. I like it. It just kind of gets us an idea on everything. So, how do waves B through E compare to wave A? I don't think I have velocity on here. Oh, I do.
Yes, for the last question, for the particle, when you're asking velocity, what's the velocity upward and meaning or just the amount of time it takes to go from point A to point B straight across without that?
It'd be the time to go across. Okay, now, first of all, let's talk about some language on these waves. First of all, wave length is just simply the length of the wave from where it starts to where it would start repeating itself. So you can measure wavelength anywhere along the wave. So if I'm going like this and I say, okay, I'm going to start right here going up at this point, I'm going to trace out my wave, and I would get to right here and say, oh, this is where my wave is repeating itself because I'm crossing my x-axis line. So that would be one wavelength. Or you could say, well, I'm going to go here. I'm going to start my measurement here on top of this crest. I'm going to go down and, oh, I'm repeating myself up here. That could be a one wavelength. Anywhere the wave starts and then it starts to repeat itself from where you started. It's kind of a wonky way to say that. But you can go, these are called troughs down here. You can go trough to trough for a wavelength, right? Anywhere it starts to repeat. So I would do this. Let's start it right here, and then let's do this for this first one. That right there is one wavelength. So let's put that in here of how we start out. So this is, now wavelength is upside down backwards Y. Wavelength. Let me write this in. Wavelength. Now, what is my wavelength? If we use the scale up here. 2 blocks is 1 centimeter. 4, 6, 8 blocks. If 2 blocks is 1, that's 4 centimeters, right? Our wavelength here is 4 centimeters. Our amplitude is how high our wave is. So this is amplitude. This is, yes, you could do it that way. So first of all, let's figure out A here as best we can. So up here we'll figure out A. So we know originally starting out that our wavelength is 4 centimeters. Nope, sorry. And we know that our amplitude is, what's our amplitude? 1 centimeter. So how does B, so we know this much, that's given. What can you tell me about B then? Yep. So now, let's do B right here. How does B compare? What's different in B? What's different in B? The amplitude, correct? Is the wavelength exactly the same? Yes, the wavelength is exactly the same. Our amplitude of our wave is what? Yeah, so this is twice as much as wave A, and I'm going to put wave A. This is twice the amplitude. I'll put an A here for amplitude. So B is twice the amplitude. Wavelength's the same. What about wave C? What's different in C? So let's do this. Let's get a straight, put this dash line here. Let's put this dash line all the way down. So I'm going to dash red line. I'm going to go all the way down here. And now that I got my dash line here, let's fix E so it goes to the dash line. So 1, 2, 1, 2. So this should, if I match this up, I'm going up. Okay, so I got to go to here. So I'm going to match this up. So I've got to go up to here, come back down here, through here, and okay, let's go back up. C, what's different? What was different in C? Nope. What's the same in C? The amplitude. What's different? The wavelength is, the wavelength is 2 centimeters, isn't it? So our wavelength here, our wavelength is half, isn't it? C has half the wavelength. So C is 1/2 the wavelength. Well, now let's talk frequency. Frequency is how many waves per second. If we look at this, and let's say that we actually have it on here. Let's go to this. If it takes 1 second to go 1 block, what is the period of each wave? Okay, 1 second to go 1 block. The period is how much time for 1 wavelength. So what is the period of each wave? How long does it take? How long does it take? So let's fill this out right here. Actually, you know what? Let's just do this darn thing in order. What's the amplitude of all the waves? What's the amplitude of A? 1 centimeter. B is 2 centimeters. What is the amplitude of C? 1 centimeter. And D is 1/2 centimeter. And E is, yeah, this is 1.5, isn't it? So 2 blocks is 1 centimeter. That means 1 block is a 1/2 centimeter, correct? One block is 0.5 centimeters. E, we've got 1.5 centimeters. What are the wavelengths? Now we did A. A is 4 centimeters. B is 4 centimeters. How many centimeters here? 2 centimeters, right? So here my wavelength is 2 centimeters. So B 4 centimeters, C is 2 centimeters. What is my wavelength in D? Well, you could say that this is half a wave, and you double it, right? Or you could go the whole thing. So if half a wave is 1, 2, 3, 4, 5, 6, 7, 8, then a full wave is 16. How many centimeters? 8 centimeters. So our wavelength here is 8 centimeters. And for E, what is our wavelength? Looks like it's 1 centimeter, isn't it? It's 2 boxes. To go here, right there's a half a wave. It looks like that is, it takes 2 boxes for the wave, and 2 boxes is 1 centimeter. Okay. If it takes 1 second to go 1 block, what is the period of each wave? Now, this symbol now, let's go back up and put our symbols in. Amplitude is A. Wavelength, upside down backwards, Y. Period. Period is T, and period is seconds per wave. That's the unit. Seconds per wave for a period. Capital T. That's the amount of seconds for 1 wave. So, if it takes 1 second to go 1 block, what is the period of each wave? One second to go 1 block. So in A, the amount of time to get 1 wavelength is how many blocks? Looks like it's 8 blocks, isn't it? So this is 8 seconds. What is B? 8 seconds. What is C? 4 seconds, right? 4 seconds for 1 wave? How many seconds in 15 seconds? And for E, how many seconds? Looks like 2 seconds, huh? Now, frequency, F. Frequency is equal to 1 over the period. If that's equal to 1 over the period, all we do is flip these units then, and instead of seconds per wave, we get the number of waves per second. The number of waves per second. And waves per second frequency is in hertz. So you'll see it like this for hertz. You'll see it seconds to the -1. Why will you see it as s to the -1? Because of this math identity. This math identity that says x to the -1 is the same as 1 over x to the +1, right? Well, if you end up with waves per second, and you don't put the word waves in there, seconds is in the denominator. That's your s minus 1, isn't it? So hertz is, when you do frequency, you got to have seconds in the denominator. Right? So if we take 1 divided by our period, 1 divided by 8 is point. No, they just, the waves is assumed. So this is going to be 0.125 hertz. 0.125 hertz. .25 hertz. One divided by 16. 0.0625 hertz. And 1 divided by 2 here, obviously we should get 0.5, I guess, hertz. Now, if frequency is 1 over the period, this period can also be 1 over the frequency. Same thing. They're just reciprocals of each other. Now, what units do we need for velocity? Meters per second, right? Where do we get meters out of this thing? Where's our meters? Amplitude and wavelength. So we want wavelength will give us the meters, the length of the wave. How do we get seconds in the denominator? We could do this. Velocity would be meters per second, like that. V is equal to lambda f is how you typically see it. Or V is going to be meters divided by the period. Same thing. The units for this then are going to be in what? What is my wavelength in? This is going to be centimeters per second. Centimeters per second. Just in this case. Usually it's going to be meters per second. Well, what's my wavelength? Or excuse me, what's my velocity? Sorry. What's my velocity? So A is 0.5 centimeters per second. What's B? Same, right? What's C? What's D?
Yeah, that's what I thought.
Yep, 2 divided by 4 should be 0.5, right? And 0.5.
Hey, I'm betting that E is 0.5.
It is 0.5
Why?
because I know the guy that made this sheet out.
Well, he needs to explain how he made all
Now,
the velocity.
you cannot change the speed of something unless you change the medium it is going through, or tension on a string or something. But so this could be sound. You are not going to change the speed of sound. Can you change the amplitude? Sure. Hit that drum harder, right? You hit the drum harder, it changes the amplitude. Now, let's talk about the most familiar thing you probably know about, which is sound. And let me grab Let me just do sound. Because this is what you're familiar with. Okay? So, this, if you've seen this before, this is just a drum head, right? This, everybody can feel that from here, right? You can all feel that? Yes? You can feel that for sure from there? Do you feel that from there? I don't need to use the targeting. I already shot you. Now listen. This vibrates back and forth. This is a speaker or a drum, right? Now, these, what did I shoot you with? I shot you with air, right? This is no different than a speaker vibrating back and forth, correct? Now, when that speaker vibrates back and forth, it's pushing air towards you when it's coming this way, and when the speaker goes back this way, it's creating a vacuum area, and it's just vibrating back and forth. So sound is just a push of air. It depends upon how many vibrations. Now, you can hear, some of you in here can probably hear 16,000 hertz, which means this thing is vibrating back and forth 16,000 times per second. And to put out a frequency of 16,000 times per second, you better have a little small cone that can do that, right? Now, older people in this room won't be able to hear 16,000 hertz. No way.
Tell me why.
Bob, you can't hear crap. You will never hear 16,000 hertz. So they say human sound cuts off at 20,000. What can hear something at a higher frequency than 20,000? Dogs, right? I've had those dog whistles before. I don't think they ever worked. Now, my hearing is messed up. I've had tubes in my ears, and I've had hearing damage. And I went to the doctor in Mondovi one time. This is true. My second teaching job. It's 1990 or 91. I go to the doctor in Mondovi. Yeah, I'm old. I go to the doctor in Mondovi. Old Doc Wright looks in my ears, and he goes, "You got FUE." First time I ever met him in my life. He goes, "You know what FUE is? Effed up ears." It'll hurt if I go to a concert close. Now, this rush of air that goes into your eardrum will give you permanent damage. There's no going back. You cannot repair the hair-like follicles in your ears. So those car next to you that's shaking because the bass is going, there's no going back. My hearing's not the best, but I grew up with tractors and all kinds of stuff that it was just loud. So this air rush that's going into your ears, and it's no different than if Bob had hair on his head this an inch long, and you sat there, I sat there and did this on the hairs on the top of his head, it's going to keep moving those hairs, and eventually it's going to rip them out. You constantly blast his top of his head, those hairs are going to get damaged and stuff like that, and they don't grow back. I mean, it's not like you can't fix it. So hearing loss is permanent. Now, so if you have, a fancy speaker system, you've got these little tiny ones maybe here, or you have a horn, then you've got some medium ones, and then you've got something like this. You would have 3 different speakers. These big ones down here are going to push a lot of air towards you, correct? It could make you shake and move. So this is your bass, right? This bass is going to be like 20 hertz to, I don't know, 500 hertz maybe. But then you need a cone that can vibrate more times per second. So this right here would take over from 500 to maybe 10,000 hertz. And these small ones up here, tweeters, 10 to 16,000 hertz. Obviously, you can't have these big speakers vibrating 16,000 times a second. There's no way. That won't work. Oh yeah, you can't get any sound out of that. If you only have one speaker, it's supposed to be able to do most of this, but it never is going to sound great. Now, if you look at the makeup of your speaker, because most people can relate to sound, beware now. I'm going to draw, it's going to be an expert artistic drawing now. This is your speaker. This is an electromagnet. Let's see if I could do this. Yeah, I could do this. I could do this. Okay, here's my speaker. You got some electrical windings back here. This is wrapped in bell wire. You've got your power coming in here. And what that power does is it energizes the magnet, and it sucks it in and constantly sucks it in, releases it, sucks it in, releases it, sucks it in, releases it, right? Then, once it releases out this way, this is the same as hitting a drum head. If you hit a drum head, especially a drum that's going like this, if you hit your drum head, your drum head, if you hit it, it's going to get forced in under tension, and it is going to flex back out, right? Your speaker can get sucked in and released. So what happens when it comes out is it's pushing this air. When it comes out, it's pushing air. Then when it sucks back in, you're going to have a gap here of very few air molecules. And then boom, it comes back at you like this. So as it moves in and out, the bigger the speaker, the more air it's pushing at you, right? Which means big bass speakers. You can sit there and shake your car and all that stuff. So when I shot you with this, again, that is the big bass speaker. So sound is all based upon frequency. So this 277.1 hertz. $288, which means this. Let me get something. Okay, check this out. Look at the length of these. Let me zoom out. Versus the length of this one. Why is this one so short? It has a higher frequency. We need that sucker to vibrate faster. Now, your first vibrational frequency that you probably did as a kid is when you took a 12-inch ruler off the edge of a table and you flicked it and made it vibrate, correct? The doorstop. Oh, yeah, the spring, yes. Yes, the spring, but you couldn't change the length of that spring though, but yes, a doorstop. I know exactly what you're talking about. I'm trying to find a 12-inch ruler. I didn't have one. But you could tighten that ruler up, right, depending upon where you held it, and you could change the frequency. So when you hit one of these, all you're doing is this is going to push in, it's going to come back out. This is allowed to vibrate back and forth and push the sound at 277 hertz. So if I hit this with this, it's vibrating. And all you're doing is making this vibrate. 2000, you can hear it probably better than me, but yeah, I had a little speaker thing. I haven't gotten it out for a while, but I can actually take a speaker and just start turning up the hertz till it gets higher and higher and higher. And there'll be people in here, I'll just say, raise your hand when you can't hear it anymore, and then pretty soon the hands will come down. But the problem is when I do that, my freaking ears hurt. So I don't do it anymore. I have to put maybe somehow to do it. But my ears will hurt for... What's that? It'll give you headaches.
In the newer movies, since this new computer digital technology that things come out, there's subliminal, what we would call subliminal messages. They have subliminal, but there's subliminal tones that make you excited, happy, nervous. The brown pants.
All right, let's finish this up here. How does this compare? How is C looking here compared to A? The amplitude's the same, the wavelength, it is, if it's half the wavelength, it is twice the frequency. C has two waves in the same amount of time as A, right? If this is twice the frequency, which is half the wavelength. Now, what about D? D has, what about the amplitude? D has half the amplitude. What else? Twice the wavelength. But if you have twice the wavelength, you only have half the frequency. Now, what about E? E has a quarter wavelength. What about amplitude? Yeah, it's a half a centimeter more, right? So amplitude-wise, it is 1.5 the amplitude. The wavelength is it's a fourth of a wavelength, but you get a heck of a lot more waves here, right? Now, oops, that's because there's too much black. So this is 1/4 the wavelength, but 4 times the frequency. They're reciprocals of each other. Now, here's my point. We can change the frequency of our sound. You can change the bass, you can change the treble. That changes the wavelength and the frequency. But it never changes the speed of sound. In here, and when we get all done, the speed is exactly the same. If the speed is exactly the same, if you mess with the wavelength, you are automatically changing the frequency. If you cannot change the velocity of that wave, which you cannot, if you mess with the wavelength or the frequency, the other one is going to... Well, in this example, it is 0.5. The speed of sound is 1,100 feet per second. It is going to stay 1,100 feet per second for the most part, give or take. Can you change the frequency and the wavelength? Absolutely. But if you change the frequency, the wavelength is going to change. If you change the wavelength, the frequency is going to change. Because you cannot change the speed of sound unless you change what it's going through. Okay, so that just gets us an introduction to waves and all that stuff. So we will...
16, right?
Yes.